presentation. Yeah. Now we have got all the basics to start the unit 3. That is Vigo notation is one of the basics, and secondly doubly linked list. So having the adequate knowledge of Vigo notations and doubly linked list, let us step into the unit 3. And in the previous class, I also showed that what are the labs which are supposed to cover. So tree traversal is one of the labs, and that will cover in this particular chapter. Out of the, I think 8 or 9 labs, we already covered 5 labs, and in this unit we'll cover the 6th lab. So that leaves us, I think, only 2 labs for the entire semester. Now, as you see, the third unit has got binary search tree. The definition of the binary search tree, the implementation, the operations. In the operations, we have searching a particular node in the binary tree, insertion in a binary search tree, and deletion in a binary search tree. Then there are certain techniques like AVL tree. Again, the definition, height of AVL tree, operations, insertion, deletion, and searching. Then there are 2 more. Red-black tree is one, and the split tree is another one. All are very interesting. And as we grow into the subject, you will find that it is one more type of a data structure. So let's start with the binary search tree. But before we straight away go into the binary search tree, actually the syllabus should have specified that directly starting with the binary search tree is unfair on the part of the students, as well it is incorrect on the part of the faculty also to say that I'm starting directly from the binary search tree. So what is a tree should basically first should be understood, right? What's a tree should basically be understood. So let's first start from the basics, that tree as per the data structure means what, right? We know the arrays, the structure of an arrays, we know the structure of a structure, we know the structure of a linked list, we know the structure of a skip list, we know the structure of a hash table, right? So also let's first understand what are the basics of a direct data structure, which is termed as trees, right? Now in the nature, what you see, the tree is like this, right? In the upright position, we know that the root is under the ground, root is below the ground. Then there are leaves which are terminating the parts of the tree, right? The end parts of the tree are nothing but the leaves, and there are branches. There's a root. From the root, the main trunk comes, and from the main trunk, there's a left branch, there's a right branch, and in the left branch also, there's one more left branch and the right branch. And this is how we have seen the tree in the nature, right? So the terminology has been picked up from what we see in the nature, that is trees. But it is not a kind of an entity here, right? It's not a kind of an entity, tree entity. No, it is a tree is a terminology used for a data structure, right? It's a terminology used for a data structure. So now let us see how data structure tree looks into it, right? You must have seen the basic difference. Yes. What is the basic difference between the previous slide and this slide? Okay. Inverted, other way around, upside down. Yeah, good. Upside down, inverted, and this is how the computation, that is the science of computers, it looks the tree exactly upside down what is in the nature, right? So in the nature, the leaves were above the ground, right? And the leaves were the visual factors, and the leaves were at the top. Now, unlike that, in the computation, that is in the computer science, the root is at the top. The root is at the top. So there are, firstly, there's a data structure, right? So we'll go from the known to unknown. First is the root, right? The root is one of the terminologies. Now I'm slowly introducing. Now this root, don't look at this root as a root in the nature. Now let's start looking root as the data structure terminology, right? It's a node. It's a node. What is in the linked list? It's an extension of a doubly linked list, but in the arrangement in which this tree structure is created makes a difference, right? It's an application of a doubly linked list, but how this entire uh, nodes are connected in the linked list, we so far we have seen it's in a serial way. There's a first node is connected to second node is connected to the third node, and the n minus one node is connected to nth node, right? So in a linear fashion, we are linking it up, right? But unlike that, this is the first time that we are not going to follow a linear fashion. For example, in the arrays also, index 0, index 1, index 2, right? So we go, if at all we have to search, we go in a linear fashion, incrementing the index. In the linked list also, from starting from the very head node, that is the very first node, in a linear fashion, we go from one node to another node in a linear fashion. But this is the first time that we are not going in a linear fashion. This is the first time that we are not going in a linear fashion. The advantage is to reduce the time for searching. The advantage is to reduce the time of searching, insertion, and deletion. So that is how this particular data structure has been invented. So root, right? Look at root as the root node in a linked list. Then subtree. Subtree means what? It is also, if I consider this as root, then it has got the branches, right? It has got a left branch, it has got a left branch, it has got a right branch, right? So this actually is a, from the root is a tree, but when you come over here, again there is a subtree, right? From here, if I consider this as a root, then there is a left branch and there is a light subtree. So also, if I come this side, right, again there is a subtree, and this becomes the root, and for that this is the right branch and this is the left branch. So in this recursive fashion, you can always consider that every part is a tree only. Every part is a tree only. I'm slowly and gradually pushing you into the ultimate algorithm which we are going to follow in today's class. Next, we have internal nodes, right? Nodes, internal nodes. What's an internal node? I'm not taking this as internal node, but somewhere in between, I'm taking the internal node, either this or this, right? So any observation, what internal node. So we are going to replace all this with our doubly linked list, right? So in the doubly linked list, right, I'm not coming here and saying internal node, right? I'm not coming here as saying internal node, but I'm coming here and saying internal node. Yeah. What could be the internal node? Any guesses? Right. Where the subtree starts. Okay, Rohan. Internal node. Internal node. One logic has come, or one guess has come, where the subtree starts. Multiple students are trying out, so let me give some time for them to punch in. No? No takers? No takers? Come on. Okay. Nandini is saying it connects the subtree to the root. Okay. Left and right of main root. Okay. Side, yeah. Fine. So internal node, uh, uh, Pranit is saying where two subtree merge. Okay. The internal node is one. The internal node is one, which has at least one branch, right? At least one branch means it has got one descendant. It has got at least one descendant, right? It has got at least one descendant. It may not be two, it may not be three or more than one, but at least one, right? That is called as internal node. That is called as internal node. Therefore, very carefully, I have brought it over here that it has got at least one branch coming here. This has got at least one branch going here and here, right? So that is what is your internal node. Now coming to sibling, right? Sibling, any guesses? Very simple. Sibling means what? Those who have common parents. Those who have common parents, right? Sibling, brothers, right? Brother and sister. Okay, you are called as siblings because you have only one parent. You have only one parent. Okay, that is a sibling. And then are the external nodes. We have seen the internal nodes. Internal node, there is at least one left branch or right branch or more than one branches are there for the internal node. Whereas external node is the leaf, right? Leaf means what? Below that, there are no nodes, right? One of the example is this the leaf or this leaf or this leaf, right? So the external nodes are the one which will not even have a single node, right? Below it, right? It's not going to be a parent of any child, right? It is the last kind of a node in the entire data structure. So root, subtree, internal node, sibling, external nodes are some of the terminologies. I'll introduce all the terminologies, but just to compare this with the tree in the nature, the tree in the nature, firstly it is upside down and the root is the starting point. From the root, everything is branching. From the root, everything is branching. So the structure, the the this particular data structure is helpful in a kind of an organizational chart. One of the application of this particular tree data structure is to define an organizational chart. As you are seeing it on your screen, there is one company called Computers R, which is based in US, right? The company called as Computers R, which is based in US, and under the company, under the director, there is one sales branch, one manufacturing branch, and one R&D branch, right? These are the three kind of a say branches. So sales, manufacturing, R&D are the internals. Do you agree? Sales, manufacturing, and R&D are the internal nodes. Out of that, R&D is the external node, right? Not R&D. Sales and manufacturing are internal nodes, whereas R&D is not an internal node. It's a leaf because R&D doesn't have a single child under it, right? Doesn't have a single child under it. Whereas sales and manufacturing are internal nodes. Now, this is maybe having, now these are having three children. Now, if you come left, now this acts like a subtree itself. This acts like a subtree itself. So just forget about this. Imagine this as root. Imagine this as root. So under the sales, US, international is the other two branches, and under international, Europe, Asia, and Canada, right? So this itself can be visualized as a tree. So also this itself can be visualized as a tree. And of course, the entire thing is a tree itself. So in a recursive fashion, in a recursive fashion, if I start from the root, if I go left, recursively, again this becomes the root, and when I come over here, again this becomes the root, there's a left and the right, the left and the right. So this is how we can also define tree in a recursive fashion. So what's a tree? A tree is a finite, non-empty set of elements. Tree is a finite, non-empty set of elements. There are no blanks. There are no voids over there. Every node is filled up. So it's a non-empty set of elements, right? Now it is an abstract model of a hierarchical structure, right? Isn't it? It's an hierarchy that the topmost is the director, then the sales, manufacturing, and R&D. Under the sales, this, under the manufacturing, laptop and desktops, right? So everywhere, if you take this as a tree itself, so there is a hierarchy. If you take this as a tree itself, there is a hierarchy, right? So it's an abstract model of a hierarchical structure. What is an abstract? Abstract has got properties, as abstract got some properties, and it will, for example, you studied stacks, right? The stack also has had a property like push, pop, peak is full, is empty, isn't it? So also this tree structure has got is an abstract data type, is an abstract data type which has got its own set of properties. Now consists of nodes. There's a node, there's a node, there's a node with a parent-child relationship, right? Consists of a node with a parent-child relationship. So left, middle, right, right? The youngest child, the middle child, and the elder child, something like that. So consists of nodes with parent-child relationship, right? Parent-child relationship. So you have to visualize this, that the base address of this must be stored here. The base address of this must be stored here. The base address of this W linked list must be stored here, right? So I should be able to go from the root to the leftmost child. I should be able to go to the middle child, and I should be able to go to the rightmost child. So also from the child, I should be able to go to my root. I should be able to go to my root. So this is how we are structuring. This is how we are structuring. So though presently I am putting it in a fashion which you generally see on ground, that is even our college, we can have a hierarchical structure, say director, then the admin branch, then the training branch, that is the and the examination branch, right? So again, under the training branch, there are CSC department and IT department, and like that. So that's another example of a tree structure. So that's the reason why I'm saying abstract, and anything which falls under this kind of a structure, we can, that abstract we can implement for that particular say organization. Is R&D an external node? Yes, Raghavendra. R&D here is an external node. Europe is an external node. US is an external node. Asia is an external node, and Canada is a external node. Whereas sales and manufacturing are internal node. So also international is an internal node. So also international are the internal nodes, right? So applications. So in common, in I mean, laptop is also a external node. So also desktop is an external node. Yes, Saurabh. Right. Application. One of the application is organization chart, as you are seeing it over here. Second is file structure. File structure means I'm coming to the computing, right? In the computers, we have one root directory. Under the root directory, you may be having academics directory. In the academics directory, you must have created a data structure directory, right? You must have created something else, right? So in data structure directory, again, there are files. Maybe you might have created PPT for unit 1, PPT for unit 2, PPT for unit 3, right? So that is what I'm talking about, the file system. File system as, as far as computing is concerned. So also programming environment. Programming environment, how I can depict? I have the main function. I have the main function. Main function can call maybe the insert function, the search function, and the delete function. Right? The uh, the search function, the search function may call minimum value on the left, right? And it may also find out that which is the maximum value in the right. So in a programming environment also, one function calling another function is could be an example of your tree structure. Could be an example of your tree structure. Our sales, manufacturing, and R&D siblings. Yeah, I'm coming to. Yeah, Raghavendra, please hold it. I'm coming to each and every terminology, so that all students will be together. Yeah. Now let us say that this is my tree structure. A is the root, B, C, D, E, F, G, H, I, J, K. Right? Uh, I have tried to color code it. I have tried to color code it. You must have guessed based on the color code for what purpose I have color coded. Okay. So root, root. It is a special node without parents. It's a no. It's a special node who doesn't have any parent. Right. So it is a node. It is a node which can have only child. It doesn't have any parent. Therefore, it is called as a special node. Right. So in this uh, diagram, A is my root. In this diagram, A is my root. Next, sibling. Raghavendra, coming to your question. Sibling nodes share the same parents. Node share the same parents. Now here, what are they? Now B, C, D is sharing the same parent. So BCD is BCD are siblings. Now out of that, B and C are colored it in blue, whereas D are colored it in green. Right? D have colored it in green. Okay, so I hope you understood. The sibling is what? The node sharing the. There are many siblings here. The other example of siblings is, as you are seeing in the diagram, IJK is one example. Good. So also, yes. Okay. So the other examples of the siblings are EF is the sibling because it has got common parent. IJK is a sibling with the F as common parent. GH is a sibling because C is the common parent. Most of you have guessed it right. So we are on the same page. So internal node, as I told you, at least one. It should have at least one child. It should have at least one child. More than one child, fine, but minimum is one. So internal node examples: A, of course, it is a special node which is root node also. And I can also say that it is a special internal node which doesn't have parent, but definitely it has got one or more children. So A, B, C, F, right? A, B, C, and F are the internal nodes and not those which are there in green. So all the internal nodes I have painted in blue and the external nodes I have painted in green. So external node, also called as leaf, as you have seen in the diagram. So node without children, node without children. So E, I, J, K, G, H, D, isn't it? E, I, J, K, G, H, D are all external nodes. Students, this is not time pass, right? Unless we are familiar with these terminologies, we will not be able to progress further. Okay, so I'm not just saying just to cover up because from here onwards we'll talk in terms of this only. We'll talk in terms of the terminologies which are tree terminologies. So ancestors, as you know, right? My parents, grandparents, great grandparents are my ancestors, isn't it? So ancestors of a node are the parent, grandparent, great grandparent, etc. Right? So who is the ancestor of B? A. right? Who is the ancestor of J? It is F, B, and A, right? The ancestor is so F, B, C, A. F, B, C, A are the examples of ancestors because F has got ancestors, B has got an ancestor, C has got an ancestor, and uh, so for FB and C, for FB and C, A is the ancestor. That's what I wanted to depict. A doesn't have any ancestor, right? I should have colored it in a different manner. So for F, B, and C, the ancestor is A, one of the examples. Now descendants, the downwards, right? Ancestors, you go towards your parent and grandparent side, whereas descendant, you come down. Child, grandchild, great grandchild, right? For example, the descendants of A are B, C, D, right? And also the other parts. The descendant of F are I, J, K, like that. Now, depth of a node. Depth of a node. Depth of a node is the number of ancestors. The depth of a node is the number of ancestors. For B, C, and D, what the depth? B, C, D. What the depth? 1. Correct. Right? So for B, C, D, it is 1. Correct. For E, F, G, H, it is 2. E, F, G, and H. First ancestor, second ancestor. Right? First for E, F, G, H, it is 2. That is 1 and 2. Right? So starting from its own position, you have to go up to the root. You have to go up to the root. Right? So that is how we calculate the depth of the node. That's how we calculate the depth of the node. Height of the tree, maximum depth of any node. Right? Maximum depth of any node. Just listen to me carefully. 3 for IJK. Right? Maximum depth means what? From IJK 1, 2, and 3. Right? IJK 1, 2, and 3 I should go. Right? So the degree of a node is the number of children. Degree of a node is the number of children. Right? For example, for A, it is 10. Right? How? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? So the degree of A is 10. Whereas for F, it is 3. For F, the degree is 3. Okay? So degree of a tree is the maximum number of nodes. So degree of a tree is the maximum number of nodes. So these are, students, some of the terminologies which are very frequently used as far as tree data structure is concerned. Okay. Now, subtree. As I was telling you, subtree. What is a subtree? A tree consisting of node and its descendants. So I can say C is a subtree. C is a subtree. So also B is a subtree. So also F is a subtree. Right? So a subtree is a branch of a tree which has at least one more descendant from that particular point. So C subtree has got 2 descendants. F subtree has got, say, 3 descendants, like that. Okay, so that is what is my subtree. Uh, uh, the Saurabh, you are talking about the last thing, degree of a tree. Yes, yes, including itself, there are 11. So there, right? There are for A, the number of children are 10, but the degree of the tree, the entire tree, is 11. Okay. Now going further, difference between height and depth. This is always a confusion. So let me make it very clear. Difference between height of a tree and depth of a tree. So if we take this as an example, Now the depth of this root node, right, backwards, 0. Where is the height going downwards? What is height? Is it this way? No. Is it this way? Yes. So because height is the maximum depth, right? This way also there is a depth, but between this and this, the maximum depth is here. Therefore, the height is 3. Therefore, the height is 3. If you consider the example, the depth of a node, the depth of the node is the number of ancestors from the node to tree's root node, right? As I've shown over here, the depth of this particular node, you have to go toward the root, right? From that node to the root. So 1, 1. From here, 1, 2. So 2. Height, come down. No more. So 0. Height, come down. So here there's 1, here there's 1. So height is 1. Now for this, the depth is 1, but height is 2 because below that, the maximum number of children are 2. So therefore we take it as 2. So depth over here is 2, whereas height is 1, and depth is 3. Why? Because 1, 2, and 3 ancestors. Height is 0, right? Okay. So height of the node is the number of edges on the longest path. Please do not forget this, right? If you say the height is, if you go only up to here, only it becomes 2. But the height of this particular node is the longest depth, right? Here it is depth 2, here it is height 2, here it is height 3. So I should take this as the height of the node, not this. Right? So of your own, this is the structure, number of nodes, or the height of this tree, which is the root node, how many are leaves, how many are internal nodes, who is the ancestor of H, what are the descendants of B, sibling of E, sibling of E, right subtree of A, right subtree of A. Okay, so this is the left and this is right. Degree of the tree, degree of the tree. Okay, so take a screenshot and of your own, please try to attempt it because I would like to cover the more things. Okay, right, Rohan, you have started doing it. I'm happy, but take a screenshot, all of you. Take a screenshot and of your own, just refer to the notes and please answer all these questions. Now, we have seen trees. Now let us say binary trees, right? Let us see binary trees. Now I'm slowly and gradually coming to BST, that is binary search tree, right? So tree we understood. I hope we understood trees, right? What is the root? What is the internal node? What is the external node? What are the siblings? What is the depth? What is the height? Okay, height and depth slide. Right. Okay. So binary tree. So trees we have understood the terminologies. Now one of the type of a tree is called as binary, right? The moment I say bi, so you must have understood. The moment I say previously the tree, now here it is not bi, right? It is not bi. There were at some places there were 2, at some places there are 3. In this case, at some places nil, at some places 2, some places 3, so on and so forth, right? So bi must be ringing some bell into your mind. Bi must be entering, right? by this binary tree, right? A binary tree is a tree data structure, right? It's a typical type of a tree data structure. Yes, yes, two children. Very good. A binary tree is a tree data structure in which each node has at most, right? Therefore, I put it in capital, red, underline. At most. At most means what? Minimum how much? 0 and maximum 2. Good. Right? So that's what at most. Therefore, the name has come as binary tree. Therefore, the name has come as binary tree. So a binary tree is a tree data structure in which each node has at most two children, which are referred to as left child and right child. Okay, so one more terminology, please bear with it. Please understand, and we are going to extensively use this root, left child, right child, right? So not only maximum of two, either it could be zero, either it can have only one left child, right? No right child, or it can have only one right child, no left child, or it can at the most have left as well as right child, but not anything more than that. Therefore, the name has been coined as binary, right? For example, 2, the left child of 2 is 7, the right child of 2 is 5. Again, recursively, this is a binary tree. This is a binary tree with this as a root, say, with this as a root. So 7 has a left child and 7 has got a right child. Again, recursively, this is a binary tree with 6 as a root. So left child 5 and right child 11. Okay, but not necessary that every time it should be having 2. For example, come to the right child 5, right? It doesn't have any left child, right? It doesn't have any left child, but it has got a right child 9. Okay, the 9 subtree, the 9 subtree doesn't have the right child, but it has got a left child, right? So this is one example of a binary tree. This is one example of a binary tree. Okay, now if you compare a binary tree with a tree, is there a difference, students? Or tree, a binary tree and a tree? Yes, right? Or tree, for example, Sanjana is saying F, F sub tree has got 3 children, whereas in a binary tree, at no place we can have more than 2. At no place we can have more than 2. So that's the difference between a tree structure and a binary tree structure. Right. A binary will have at most 2. Yes, idea, but tree has no limit. Yes, you are absolutely right. There could be one or there could be more than one. Whereas in a binary tree, at most 2. At most 2. Can the parent 2? Yeah. Can parent 2 have one child? Yes, you can. If if there is no this right child, if there is no right bifurcation, this parent 2 can have only one left child. Saurabh, there are two parent 2s. There is a parent 2 here and there is a parent 2 here also. Yes, it is going to be a linked list. I'm coming to that, right? Presently, I'm just putting it in an algorithm fashion with a diagram, but ultimately, we are going to come in a not only a linked list, but a doubly linked list. Doubly linked list. Why? Because by no, by means what? Left child, right child. So you should be able to go to the left, you should be able to go to right, right? So that's how it's going to be. So I hope there is absolutely clear that this is a tree structure that which has got no limit. Any node can have one or more than one child. Whereas in a binary tree, every node can at most have 2 children. Every node can have at most 2 children, right? Now let's go further. Binary search tree, right? This is there is one more variation of a tree structure, binary search tree, BST, popularly called as BST. In most of the book, you will find BST. BST. What is BST? Is binary search tree, right? Now, as you are seeing it over here, as you are seeing it over here, it's a by, but it is search tree, right? By and search tree. So there is obviously is a difference between a binary tree and a binary search tree. So let's try to understand what is this binary search tree and how it is different from binary tree, right? It's not that only search has been added, but it has been added with few properties, right? It has been added with few more properties which are exclusively for binary search tree. For example, a binary search tree, PST, is a binary tree first. You agree with me? Because every node can have at the most two nodes, right? A binary search tree is a binary tree first in which the nodes are assigned values with the following restrictions, right? That restriction was not there as you have seen in the previous slide. That is a binary tree. A binary tree, only one restriction was that every node can have at the most two nodes. Every node can have at the most two nodes. But in a binary search tree, there are restrictions. What are the restrictions? Right? Firstly, it's a binary tree. Every node has got at the most two nodes. Right? This has got one node and this has got one node. Fine, but at the most two nodes. That's the common factor. With the following restriction. Restriction number one: no duplicate values. Right? As Saurabh was asking me, here it was two, and here also it was two. In what? Binary tree. So if I call this as the root, I am right. If I call this as leaf, I'm right. Right? So in a binary tree, in a simple binary tree, there is a possibility of the key at the node being duplicated. The key at a node being duplicated. Whereas in a BST, that is binary search tree, no duplicate values. No duplicate values. So it's always a set of keys, right? Where there are no two keys will repeat. Point number one. What is the second restriction? The left subtree, right? The left subtree. The left subtree of a node can only have values less than the node. Which node? The parent node. Now, to 8, to 8, the left subtree is this. 3 is less than 8, so only 3 can come here. Only 3 can come here. Unlike in the other case, in the binary tree, it was 2 here and 7 here. It was 2 here and 7 here. So that restriction was not there in binary tree. But the moment I come to BST, that is binary search tree, the left subtree, the node value will be less than the node itself. Similarly here, this is also again a binary search tree. Its left node is less than the node itself. Again, this is a binary search tree. The right node is greater than the node, right? Which I have not come to. I'll come to that. Let me come to that. The right subtree of a node can only have values greater than the node, right? See, 6 is greater than 3, but because it is on the left hand side of 8, it is less than 8. I hope there is no confusion. The right subtree cannot exceed 8, right? This value cannot exceed 8. You cannot say that, sir, the only restriction was it should be greater than 3, right? But we are branching from the node. The root node is 8. So anything on the left of 8 has to be less than 8 first, right? But this is a binary search tree again. So same rule applies. The left one is less than that and the right one is greater than that. But though greater, but definitely less than the descendant node. Definitely less than the descendant node. Now here also, why is it like that? Yeah, why is it like that? Raghavendra, it is it is for the simple reason that ultimately we want to do the insert, search and delete faster and faster. Insert, search and delete faster and faster, Raghavendra. since you asked the question, I'm search is faster. Aman, Jolly, yes, I agree with you. Good. You have answered it correctly. But let me, since Raghavendra has asked, I was trying to take it little later. But since the point has come, since the point has come, see, suppose I want to search for seven. I want to search for seven. Now, if you see the number of descendants, so 1, 2, 3, 4, 5, 6, 7, 8, right? If I put it in a linked list fashion, if I put it in a linked list fashion with this as 8, and I'm looking for 7, so I have to go and one more like this in a linear fashion, right? Whereas if I'm looking for 7, the all the nodes which are on the right of it are straight away eliminated. All the nodes which are on the right of it are straight away eliminated. So I have brought the search down by 50%. N by 2 it has become, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes are there. So the moment I say 7, I have straight away reduced 4 nodes. I have straight away reduced 4 nodes, including this, it is not here, right? When I come over here, 3, right? Anything on the left hand of 3 is definitely not 7 because it is less than 3. So I have eliminated all this branch, right? Again, when I come to 6, right? I'm looking for 7. So again, anything which is on the left of 4, left of 6 is eliminated, right? So the answer to your question is why this restriction of left being less and right being more, right? Unlike in the binary tree, I have to visit every node and look for 7. I may fail entirely over here. Then I need to come to the right branch of my binary tree and look for 7 here. Are you getting my point? So to make the search operation faster, we have this data structure. So what happens? One child node contains two parent nodes. No, it is not possible. No, Nagavenkat, how two parent? Every every child has got only one parent. There is no possibility of two parents. You mean two descendants you are talking about? Nagavenkat, every node is going to have only one parent. This has got one parent. So there are no sir parents only. There is no node which has got two parents. There is no possibility only. A parent can have at the most two child, but no node is going to have two parents. It's not ulta. It can come from 8 also. It can come from say 7 also. No, it is not. The structure itself is not there. Therefore, the first restriction is what? Node duplication. Second restriction is what? The left branch will have less than the node itself. The right branch is going to have greater than the node itself. Deep God. What happens if we have 15 in place of 6? Then while searching, it does not look at left node. True. Correct. Suppose we have 15, it firstly doesn't look on the left. It goes on the right definitely. It goes to 10 greater than 15. It comes to right 14. Right? Now here it does not go to the left, but if the right branch is null, if the right now replace this with a doubly linked list. Replace this with a doubly linked list. If you replace this with doubly linked list, the left is not null, but the right is null. The right is null. So the moment I have come to 14, right, and 15 is above 14, 15 is above 14, but the right of this particular node is null. So 15 not found. Again, in the binary sort, yeah, in the binary sort, what we saw in the arrays, there is a possibility. Yeah, what we do, you sort in a binary search, right? You sort it and keep it in a binary search. So that's how we divide and rule, by divide and rule. Yes, similar to binary sort. Okay, so restriction one is this: all the left descendants of the root should be less than the right. Yes, true. Rohan, left descendants is less than the right. 3 is less than 6. True. Yes. Now, recursive definition. Recursive definition. How do I define it recursively? Because recursive logic, we are going to use it. So I thought that I'll define the BST in a recursive version. How? In a recursive, the left subtree of a node is a binary search tree. Recursively, right? The left is a binary search tree. This is a BST. This is a BST. This is a BST. Right? So also the right subtree of a node is a BST itself, binary search tree. So same rule is applicable here. When I come here, the left has to be less. The left has to be less. It should not be repeated. It should not be repeated. At the most two. Right? The one on the left is less than this. The one on the right is greater than that. So it's again recursively, it's a binary search tree. Again at 6, again recursively, it is a BST. The left has to be less than 6, the right has to be greater than 6 in this fashion. In this fashion. So recursive definition is also correct. Left subtree of a node is a BST search. BST itself. Okay. The right subtree is again a BST. So just to compare between the binary tree and the BST, just a comparison between the binary tree and a BST. Point number one, there is no restriction that the left should be less than the node, right? The left should be less than the node, that restriction is not there. Okay. Unlike in a BST, the left has to be less than the node. Point number two, no duplicate values. Here, there are no duplicate values. Here, 2 is getting duplicated, 5 is getting duplicated. 2 is getting duplicated, 5 is getting duplicated, right? Then the left subtree will have values less than the node itself. That restriction is also not there. 7 is not less than 2, right? 7 is not less than 2, like that. So this is a difference between your binary tree and binary subtree. Then how all leaf descendants are less than root? In which you are talking about, Rohan? Leaf descendant is less than root. It will be on the left hand side, all the leaf descendants will be less than the root. You are talking about, Rohan, you are talking about what? 13 is the right descendant of 10. Yeah, so 13 is the right descendant of 10. So this leaf, see, anything which is on the right hand side has to be greater than this. So right of 10 is 13. So it is coming to the right only. Okay, right. So I hope, because see, if some student has skipped BST and he has attended or learnt only BS, that is binary tree, BT, right? He may say maybe searching in this tree is binary search tree. No, the terminology names binary tree does not have any restriction except that every sibling, every node has got at the most two nodes. That up to that only both these match. Up to that only both these match. But other than that, there is so much of mismatch. There is no restriction that left should be less than the node itself or right should be greater than the node itself. That restriction is not there. duplicate values, that restriction is not there, right? So only BT is same as BST. No, BT is not same as BST because these all restriction 1, 2, and 3 restrictions are there on BST which are not there on BT. Okay, so students, please do not get confused. Now let's come to the binary tree traversal. Binary tree traversal. Now so far, linked list, whether singly linked list or doubly linked list or arrays, what we have done, we have gone in a linear fashion, right? Unlike linear data structure, for example, index 0, index 1, index 2, index n, we have gone so far. Linked list, starting from, so always we are having a special pointer which points to the head node and a special pointer which points to the tail node, isn't it? Whether in single linked list, double linked list, circular linked list, right? So it is a linear fashion. Queues, queues also linearly we go. Stacks also we go linearly. So unlike that, which have only one logical way of traversal, then tree can be traversed in a different way. As there's a spelling mistake, let me correct the spelling mistake here itself. Uh, which have only one logical way to travel. Oh no, there is no spelling mistake. Traverse them. Yeah, it's correct only. It's correct only. See, which have only one logical way to traverse them. Means what? Arrays, linked list, queues, stacks has got one logical way of traversing, that is a linear way. Trees can be traversed in different ways. Trees can be traversed in different ways. Now, what are those different ways that we are going to learn now? Following are generally used ways of traversing means what? Going from root node to the leaf node, right? Traversing means what? Always the starting point is root, right? And from the root itself, we are going to traverse. Okay. So the first one, okay, let's take this as an example. One, now this is a binary tree, this is not a BST, right? The example, because the left branch is higher than the node. So, and therefore I have given the heading as binary tree, not BST, right? In BST also is applicable. In BST also is applicable, but uh, the example which is in front of you is a binary tree, not BST. So, keeping this as an example in front of you, the first way is called as in-order traversal. In-order traversal. Now, in in-order traversal, you always go to left, right, root, and right. Left, root, and right. So, if this is the example in front of you, if I ask you to print what is the in-order traversal, any guesses? Left, root, right. You come here again, left, root, right. Ritik Jain, 42513. 42513, 42513. Oshnima, good. 42513, Rohan. Meghana. Yes, Meghana, go for it. Meghana, you wanted to try? 425123. That is 425123. Maybe some typing error. It's okay. Good. See, in order, left, right? Come to left. Is there a left? Means is the left is null? No. Right? So then go to left. Go to the right. Go to the root. From left, right? First come to the extreme left. Go to the root. come to right. So 4 to 5, 4 to 5. Now, since we have already traversed this, right? So this much is over. So what is left now? Root. This left is over. So root is 1 and then right. So as most of you have guessed it correctly, 4 to 5 and 3. 4 to 5 and 3 is the correct answer. 4 to 5 and 3 is the correct answer. Right. The second is pre-order. Now pre-order is root, left, right. Pre-order is root, left, right. Okay, go for it. All these guys. Root, left, right. Okay. 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. Great. Good. So 1, 2, 4, 5, 3. 5. Root. What is root? 1. Left. But now again it's a subtree. So the root. So the root. That is what is the root? 2. Come to left. What is left? 4. What is right? 5. Right? So this part is over and what the left is over. So I come to right. So 1, 2, 4, 5, 3. Good. Next is post order. Left, right, root. Left, right, root. Yes, go for it. Left, right, root. So please remember this. Okay. 4, 2, 4, 5. 4, 5, 2, 3, 1. Left, right, 4, 5, 2, 3, 1. Okay, good. Right. So when I was teaching this, when I was teaching to your senior batches, right? So one of the student they came up with some the Hindi part of it. Le rori, ro ro le re, ro le ri, and he said then le ri ro, something like that. So he converted that into some kind of a Hindi part of it. Le ro ri, ro le ri. So he said, sir, I will remember pre-order is ro le ri, and this I replace with left, and this goes to right, something like that. So you have to coin yourself. You have to coin some kind of a typical way of remembering it. In order, pre-order, post-order. It's a very kind of a what you can say favorite questions of their interviewer, right? So the post-order, as most of you have guessed it right. First is left, then is right. So 4, 5. Go to the root 2, right? So left is over. So straight away go to right, that is 3, and then go to root. So 4, 5, 3, 1. 4, 5, 3, 1. So this logic, this algorithm, you have to remember. This algorithm, you have to remember. Okay? Clear? So in the trees, unlike your arrays, stacks, queues, which has got a linear traversal, starting from the first node to the last node, there was a linear traversal in the earlier data structures. Now, starting from the trees, for example, binary trees, there are different traversal techniques. So that is what is going to make the difference. Okay. Now, coming to the second part. Now, the second part, first is the definition of a BST and BT. Now, the second part is the terminologies of BST and BT. The third part is insert, update, and delete. Okay, insert, update, and delete. Now, to come for that, I am going to share the code with you. But before sharing code, you must understand each and every function and each and every part of the code. Right? The aim always is to build your logic. The aim always is to build your logic, because that logic building is going to fetch you the job. And once you get a good job, that's going to make your career and a good citizen, right? So ultimate aim is to make a good citizen. So I, it's my primary duty to build your logic. So let us start writing the code to implement what we are just diagrammatically and theoretically and conceptually we learned. Okay, right. So the structure. If you look at this, what is that? Struct node, int key. You are saving some value. Struct node, the left pointer and the right pointer. The left pointer and the right pointer. Okay. So diagrammatically, if I want to show here the structure, right? The complete structure is a block, right? So say 4 bytes for left pointer, 4 bytes for the integer value, and 4 bytes for your right pointer. So total 12 bytes with a base address. Total 12 bytes with a base address. So therefore, before starting the third unit, I introduced you the doubly linked list, right? Because you should be able to go to left and you should be able to go right. There in doubly linked list, we have used the terminologies previous and next, or you can also say left and right. Okay, because BST has got left subtree and right subtree, or left node and a right node. Therefore, here onwards for BST, the left pointer we'll call it as left, and this pointer we are going to call it as right. So this is the structure. Now the flag, why I'm using this flag, I'll come to when we are actually dealing with the delete and search jobs, insert and delete jobs. So that's the time I have globally declared flag as 0. Globally declared flag as 0. Yes, Nikhil Reddy. Anything you would like to say? Don't we need a pointer to go to parent? Yeah. How we are going to the parent? We'll see it. Nikhil Reddy, your concern is correct. Your concern is correct. But we always traverse from the root to the node. We always traverse from the root to the node. So we will be able to do it in a recursive fashion, right? Or in a logical manner, without storing the, or without making a provision to store the pointer, store the base address of the parent. How we can do it? Okay. As we grow, as we see the code, you will appreciate how to do that, right? But your point is valid, that because in the traversal sometimes left, root, right. So from left, how do I go to root, right? And from the root, when I go to right, once I finish the left subtree, how I go to the what the parent of this left subtree, right? So your concern is correct, but programmatically it can be handled, and it can be also handled in a recursive fashion. We'll come to that, but your point is valid. And I will clarify your point once we take on the code. Right. So let's say I want to create a new node. Right? So when I call this new node function, what is the item? This item is nothing but the key which we are passing. The item is going to be the key which we are passing, right? So if you call this function, obviously you are passing item, assume that it is 4. The key is 4, so you have passed 4. So what I'm doing, I'm creating an isolated node called as a temp, right? So the base address of that is say 500. The base address of that is 500. So in temp, I'm storing 500, right? So this block I am making, whose base address is 500. That is what happens exactly at step number 1. At step number 2, temp of key, right? This temp of key is equal to item, which I have passed 4. So this particular thing fills up over here. Okay, that's the statement 2. Statement 3, temp of left is equal to temp of right equal to null, right? This temp of left, the temp of right, both are nulls. So an isolated node is created and it has been initialized like that, and return temp. So in case when I want to insert, obviously I have to create an isolated node. So I call this new node function with a key value and create an isolated node. So this isolated node is not presently part of your tree structure, but ultimately it has to be made part of the tree structure, right? Ultimately it's going to be made part of the tree structure. So I hope the structure is clear and creation of new node is clear, right? In case of any doubt regarding creation of the structure and new node, please come to chat window. Otherwise, no need of saying understood. No need of saying understood. Since Nikhil Reddy has raised this point, Nikhil Reddy, in case of a tree, which doesn't have the limitation of only two children or at the most two children, there very typically it becomes very complex, and dynamically we require to vary our nodes. Dynamically we require to vary our nodes. So in that case, we definitely would like to have a thread going to the parent. We definitely want to have a thread going to the parent. So let's go step by step. What is in your syllabus? Let's first handle it. Right. So the chat window is silent. So I suppose that as far as the structure of the node is concerned, you are clear. As far as creation of the new node is, you are clear. Left is null, right is null. Assign the value to the key, and the temp is storing the base address. Okay. Now, this particular function finds the minimum value in a node. Find the minimum value in a node. Just go through this code and then I'll explain. There is some recursion which is happening. Go through this code, try to understand as much as you can, and of course I will explain it step by step. All right. So when I call this function, I am calling this function to find the minimum. What are the parameters I am passing? I am passing the address which is there in the root. Now students, I suppose you have understood the fact root need not be always only one. When you are coming to the subtree, are you getting my point? I hope I am making myself clear. Yeah. I suppose I am making myself clear. Of course, this is the root of the entire tree, no doubt. But when I branch over here, because recursively I gave the definition. When I branch over here, now this becomes the root. Are you getting my point? So if this is the base address of this node is say 1000, the base address of this node now when I consider it as root, maybe 500, right? So for this subtree, the root is at 500. For the entire tree, the root is at 1000. For this subtree, the root base address is 1500. Okay, so therefore I gave you the recursive definition of a BST, right? So when I shift from here to here, this is the root now for this subtree. Are you getting my point? So keep this in mind, because if this is clear, then I can proceed in explaining the logic. But whenever I say root, if you are visualizing, so root is 8 only. Why? How 3 is root now? Okay, then there is a problem in understanding. Then, the me and you are not on the same page. So if this point is not understood, root for 7, root for 7 is 6 and not 8, sir. Yes, yes, you are right, Siddharth. So the tree root is 8, right? And absolutely, you can say that root for 7 is 6. Root for 6 is 3. Okay. So when I step down from here to here, now this is a subtree with this as a root. When I step down from here to here, this is the root for this subtree. So this is what visually please understand and keep that at the back of the mind. Right? Once again, I say that when I step down from here on the left hand side, this is the root for this subtree. When I step to the right from here, this is the root for this subtree. Okay, so if that point is understood, then my coding you will be able to appreciate. Otherwise, there always will be a question. So the root is 8. How you are saying root is 3 now? And how you are changing the root to 6? And sometimes you say root is 6. Sometimes you say root is 3. And sometimes root is 8. Okay. Now, suppose I want to find the minimum. Suppose I want to find the minimum. And I have passed the root. I have passed the root. Now, initially, when I create the structure node, when I come to main, I make root as null. The moment I jump into the main, execution begins from main, and root, which is a pointer of struct node type, I initialize that to null. Right? Means when not a single node is there in the tree, the root value is null. You agree with me? When there is not a single node in the tree, the root is null, right? So without having a single node in the tree, if I call this function to find the minimum, so what I have passed, root value is null. If root equal to null, true, I am returning null. So far, clear? This particular function. See, when execution begins from main, struct node root, pointer root, assigned to null. So the starting point is that when I step into the main, I made the root as null. Then I built the tree, right? So when there are absolutely no nodes, then this is null, right? This is null. When this is null, if root equal to null is true, and I'm returning null. So this function is over. Point case number one. Case number one. Can we use while loop? Also, yes, we can, Yogeshwar. The other way is recursively. But while also you can use. You have to slightly modify the code. If the code size has to be smaller, you use the recursive function. But if you are not comfortable with recursive function, you can use while loop also. Yogeshwar. Right. Now, now is the root null? We have the base address of the root as 1000, so it's not null. Right? Is there a left branch? Students, I'm asking you, is there a left branch from this diagram which I am showing you? Yes. On what basis, Bhavana? Bhavana, you are saying yes. On what basis? Address. What the address there? 500. Correct. So means what? Initially, when I created an isolated node, this was null, and this was initialized to 4 or 6 or whatever, right? That time there was no left child and right child. But the fact that that null has been replaced with some value, it means that there is a left branch and there is a right branch also, because both addresses are there. So let's assume that my left child is 500. So this is pointing here. This is null, right? So also my right child is 8. Now I'm in a BST. I'm in a BST mode. The left is less, the right is more. Left is less, the right is more, right? So it's a BST very much. So I'm sticking to the BST. Now to let's come to one part. So what I have passed, when I have passed the root, so I have passed 1000, right? This value is 1000. Root equal to null. Root equal to null. What is it? Boys and girls, are you with me? False. So it is not going to return. It's not going to return. Will it come to else if? Root of left not equal to null. If root of left not equal to null, what am I trying to do? Find minimum. Should I go to right? Should I go to right? Why should I go to left only? Why should I go to left? Why can't I go to right? In the logic, I'm just saying root of left. There is nothing like root of right. All values to the right are greater than 6. Good. Exactly. Exactly. Right? So, Raghavendra, when you ask me why this is this restriction of less, right? Since the value which I am searching, the value which I am searching is less than that. So there is no point, means let there be 1000 nodes on the right hand side. I simply ignore all those 1000 and do not unnecessarily waste my time in going to the right side, right? Because 100% it is not there on the right side. Okay, Raghavendra? So I am only interested in root of left not equal to null. So here, when I question 1000, root of left is 500, not equal to null, true, not equal to null, true. So node with minimum value, there is a possibility here. If there is some more tree, you have to go further down. But at the present, let's consider the simple case, true. What I do, recursively I say return, but I call the recursive function find minimum. I'm calling the same function root of left. So what am I passing? What am I passing here? 500, right? I call the same function 500, right? I'm calling the same function and 500, right? So 500 not equal to null, true. So the return value, sorry, what is this? Else if root of left not equal to null. Is this true now? Root of left not equal to null. True or false? False. Why? Because root of left, I have already come to 500. 500's left, how much? Null. So root of left not equal to null is false. So what do I return? I return root. So what is root? 500. So this function has come to the minimum value, which is 4, and passed the base address of this particular structure. Clear? Are you okay? Anybody who is not okay, please come to the chat window. Anybody who is not okay, please come to the chat window. Meghna, I know you will understand. Anybody who is not able to follow why I am coming to the left, I am finding minimum. Therefore, name find minimum. Why are we using return value as addresser. Yes, Bogaram, it is like this. It is like this. Presently, I am considering only say one key, but not necessarily it can have an. I can replace this with entity. Entity means what? Is student. Student means what? Roll number, name, mm, branch, blah blah blah. Right? It can be replaced by a number of things. When I pass the root, from the root, from the root, base address of the root, I can find who is on the left, I can find who is on the right, I can find anything which is described over here. Anything which is described here. So when I return this, from that I'll say minimum is 4. Right? So the basic thing I'm passing, from the basic thing I can find out anything which is there at this node. So for that purpose, Bogaram, we are returning the base address. If right of 6 is 9 and left of 9 is 3, then mu1 is 3. What 3 no sir? Bhuvan Sai Reddy. Bhuvan Sai Reddy. This 3, what you are visualizing on the right hand side, will never come. Bhuvan Sai Reddy. On the, you are thinking 3 is less than 9. True. But at the first step, 3 is less than 6. So it will not go towards 9 at all. It will come to the left side only. This 3, it will not go to the right where you may find 9 over here, say 9 over here, and maybe 3 here. This case will not happen only. This case will not happen only. When you have 9, when you have 3, that 3 obviously has to come here. On the left of 4, you will have 3 here. On the left of 4, you will have 3 here. Right? So that possibility, initially those doubts will come. What Bhuvan Sai Reddy has got, even we also used to have those doubts when we were studying this. So a very pertinent doubt, very important question. So, but the BST structure is such, when I'm inserting 3, I'm not going to right side only because the root is 6. So obviously it has to come to the left side. So students, I'm stopping at this particular point. On Friday, I'll consider few more functions are there. I think there are 3 or 4 functions. That is, insert is a function, search is a function, in order search is a function, and delete is a function. Of course, main is also there. Shankar, can we have the quiz next class?
Yeah, okay, sir.
Engagement of the students. I hand it over to you. If the students are free after that, you can go ahead with the quiz. Shankar sir, the students are free,
Yeah, okay,
you can
sir.
go ahead with the quiz. They are not free. Yeah. Any questions, students, so far? As far as this minimum and create node is concerned. If there are questions, please ask me. We have another class at 2:40. No, sir, we have another class. Okay, so sorry, Shankar, you may have to take the quiz in the next session.
Okay, sir.
Okay, so thank you, students. See you on Friday. See you on Friday. Tomorrow you have got a class that will be conducted by your own faculties. The class will be conducted by your faculties. So please clarify any doubts which you have with your faculties. Thank you. See you on Friday. Have a nice day.